T1 cosine theta, what sign should I put in front of this term? Is my rope pulling up or pulling down? Basically what I'm asking. Up. And my positive direction is upward, so positive sign to put this one. So T1 cosine theta. Same thing with my second rope. My second rope is pulling up, so this is T2 cosine theta. Now, gravity, what sign? Negative, right, yes. So as we go through writing these equations out, we need to constantly be referring back to our free body diagram to make sure that we get the signs correct when we write out the terms. I can go about solving this. We saw that T1 is equal to T2, so I can just fill in that here. So T1 cosine theta plus T1 cosine theta. I can move my mg over to the other side. So T1 is equal to mg over 2 cosine theta. Or 2T1 cosine theta equals mg. So I kind of skipped a step. There's the extra step, and we end up with T1 is equal to mg over 2 cosine theta. And now it's just a question of filling in everything that I know. So we said here that our mass is 20 kilograms. Our acceleration due to gravity is 9.8 meters per second squared. And this is 2. And now we said cosine theta is equal to 2/3. So for cosine theta, I can just fill in 2/3. Or if y'all don't like that, you can go ahead and put in cosine of 48 degrees, and it'll give you the exact same answer, but it's just a shortcut. And this gives us a tension of 147 kilograms meters per second squared. What's my SI unit for force? Newtons. Newtons, right. So 147 newtons. 1 newton is 1 kilogram meter per second squared. Okay, yes, please.
So, is that only 5? So that's the total tension on the whole thing?
That's the tension in each rope.
So do you double that to get the final answer? Or
In this case, no. So let me read through the question statement again. The question statement says, what is the tension in the cables?
okay.
So, yeah, so each cable is going to have a tension of 147 newtons, and that's the answer we're looking for. So this is T1 equals T2 equals 147 newtons. Okay. Anything else here? Are we all disconcerted by the fact that I filled in 2/3 for cosine theta and want me to backtrack on that a little bit? Did I hear one, please? I hear mumbles. All right. So, I could have certainly done this. 20 kilograms, 9.8 meters per second squared, 2 times the cosine of 48 degrees. That's actually what theta is when we go through and actually take the arc cosine of 2/3.
Also, if you
Just like this, and that'll give us our correct answer. Okay, one other comment? Okay, y'all are talking behind my back when I'm not looking. So this is an example of doing a problem in static equilibrium where there's no motion at all. Problems with dynamic equilibriums work exactly the same way. It's just the fact that they're actually moving at some constant velocity. That still, when we're talking about equilibrium, the net force is zero. Whether it's static or dynamic equilibrium. Okay, so I'm going to do an example problem with dynamic equilibrium. I wanted to go ahead and write this one out for y'all because there's a lot of information here. This is in the chapter problem number 31. In 31, it says we've got a 500 kilogram piano that's being lowered by a cable. We've got two people on either side of the piano that are pulling at it with ropes at some angle. And their purpose is to keep the whole thing steady. They want it to move at a constant rate. They want it to move at a constant velocity, basically. They don't want any acceleration at all on the piano. They don't want to wreck it. So the problem statement gives some specifics. It says Bob's rope pulls to the left 15 degrees below the horizontal with 500 newtons of tension. Ellen's rope pulls toward the right 25 degrees below horizontal. And then it asks the questions, well, what tension does Ellen have to supply on her rope? And also, what is the tension in our main cable that's lowering this piano down? I'll leave this up here for just another minute or so. So I'm just going to write down some of the information that we've been given here. Mass is 500 kilograms. And we have two people steadying it with ropes. So we've got this piano being lowered down. Got Bob and Ellen and the piano, and then some cable up here. So there's our picture. Go ahead and throw in our coordinate system, x and y. Okay, and then of course we know that the next step after drawing this picture is what?
Free body diagram.
Free body diagram, yeah. So we represent our piano by a particle there. We look at the various points of contact on our piano. We see that we have three. We've got the cable, we've got Bob's rope, and we've got Ellen's rope. So our cable is going to be pulling upwards with some force to counteract gravity. We've got Ellen over here. We've got Bob over here. Called the tension for Bob, T-Bob, T Ellen, and our T cable here. So those are all our contact forces. And then, of course, we need to look at the long-range force. The long-range force, again, is gravity. So we've got some force due to gravity here as well. And we can write out the principles that we're going to be using to solve this problem. This looks a lot like dynamic equilibrium. Newton's first law and our principle of superposition. Our principle of superposition just states that our vectors, our force vectors here, can be added together. And we want to write down our knowns that we've been given. In this case, Bob's supplying 500 newtons of tension, and our mass of our piano is 500 kilograms. We want to find here the tension of Ellen's rope and the tension of the cable. So I've kind of got my whole problem set up here. Now it's just a question again of solving it. You know, where do I go from here? So now, what do I do?
Break up the tension forces into X and Y components.
Yes, absolutely. Thank you. So again, my strategy: basically break into X and Y components. So we'll look here at Bob's tension. TBX and TBY. And we're given that this angle right here is 15 degrees. And I guess for the sake of completeness, I should have put those on there. So now that I've got that, what's the X component of the tension due to Bob?
500 cosine 15.
Yeah. So TBX equals TB times the cosine of 15 degrees. And then, of course, because we know we use cosine for the X component, that our Y component must be the sine of 15 degrees here. And I can do the same thing with Ellen's. And yeah, I know my angles are all messed up, but obviously that's not 15 degrees, but we're getting the point across anyway, I hope. So now that I've got my diagram there drawn out of my tension due to Ellen, or the tension of Ellen's rope, what's the X component of that tension?
The same weapon.
Yeah. I think if I understand what you're meaning.
Well, there's a different sign, but
What's that?
it's a different sign, but the Newton's value is the same.
Yeah, we're dealing with magnitudes right now. So this is cosine of 25 degrees, and my Y component is sine of 25 degrees. So now that now that I have those broken down, I can actually look at my Newton's laws, my Newton's first law for my X and Y components. So here are the sum of my forces in my x direction. What all do I have for my forces in my x direction?
TB cosine of 15 and TE cosine of 25.
Yeah. So my TEX and my TBX, yeah. This is TBX plus TEX. And we're dealing with equilibrium, so this is equal to 0. So here my TBX, I see that, well, it's pointed to the left, and it's got magnitude of TB times cosine of 15 degrees. So I need to put a negative sign in front here. Negative TB cosine 15 degrees. Now my TEX here is pointed to the right, so a positive sign in front of this one. So this is plus TE cosine 25 degrees equals 0. Now, what was I interested in finding in the first place, now that I've written all this out? Yeah, okay. It's easy to lose track, so much going on here. So let's solve this for TE. TE cosine 25 degrees equals TB cosine 15 degrees, or my tension in Allen's rope is just TB cosine 15 degrees over cosine of 25 degrees. So now I just need to plug in numbers. And I end up with $533 newtons. Okay, so that's the answer for A. Let's see, for B, we wanted to find the tension in that cable that's actually doing the lowering. Well, so let's look at our Y equation. The sum of our forces in Y is going to be equal to 0. What all forces do I have in my Y direction?
Tension of the cable, tension of bob, Ellen, and the gravity.
So tension of my cable, let's see, my tension of Ellen's cable or rope in the Y direction, my tension of Bob's rope in the Y direction, and my force due to gravity. Oops, not what I wanted to do, plus Mg equals 0. So now I just need to step by step go through and fill in here expressions for each one of these. So my tension of my cable is pointed upwards, so it's going to be positive. Ellen is pulling the rope downwards and to the left, so my Y component from Ellen is going to be negative. This is negative TE times the sine of 25 degrees, which is what we found right there for Ellen in the Y direction. My tension due to Bob, again, he's pointing down and he's pulling down into the right, so this is going to be negative in my negative Y direction. So this is TB sine of 15 degrees, which is just what we found when we analyzed our forces. Broke the tension of Bob down into components. And then my force due to gravity, of course, is going to be negative, pointed in the downwards direction, negative mg. Just need to solve for the tension in the cable here. So move everything over to the right-hand side. I know all this information, so now I just need to fill it in. 533 newtons. let's see, when I do the math there, I end up with 5,250 newtons. So I've answered now both parts A and part B, so I've done my analysis. The problem's complete. Yeah, please.
Any reason the mg went from -100 to +100?
Yeah. Yeah. So I've got this equals 0. So now I'm just solving. This is my item I'm interested in. So yeah. So I'm just put this on one side, everything else on the other side. Yeah. Yeah. You know that. It just yeah. So other questions here?